Okay, so we're going to talk about other ways to make ethers besides the Williamson ether synthesis. And I want to review first how we made alcohols from alkenes, because we can modify this reaction to use for ethers. So this was back in the chapter on alkenes. We talked about where you could use mercuric acetate, and the alkene pi system would act as a Lewis base and attack the positive character mercury and spit out an acetate ion and give you the more stable carbocation. And water, as the solvent in this system, is going to surround this carbocation, so one of these can react with that carbocation coming from the opposite side of where the mercury is. And when you put a third bond on that oxygen, it gets a plus charge, which it can just lose a proton, and that's how you get this alcohol with the mercury still on it. And then in the second reaction, you put in the sodium borohydride, and at the end, and when that's done, the hydrogen will have replaced this mercury group, and so you get Markovnikov addition alcohols from alkenes. Well, one of the things that came out during this process when we kick out this acetate, here it is, here, it's a resonance stabilized anion, which is why one reason it was able to come off of there okay. But we have two things in here that make this reaction work, and one of them is the water, which is the solvent, which is not all that great of a solvent for alkenes. And the other thing is that we're counting on this acetate not to interfere and beat the water to finding this carbocation. So one of the things that people were interested in trying is trying a different solvent instead of water, because, like I said, it's not that good of a solvent for alkenes. And also, in such cases where this acetate does interfere and also react with this carbocation, we want to minimize the chances of that happening. So we're going to make a couple of modifications, and that will enable us to use this same reaction to get to ethers. So one of the things we're going to do is we're going to make an alcohol be the solvent, and it's going to be a better solvent for the alkene, and also it's going to play the role of nucleophile that the water was doing in the previous reaction. And when we do that, then we'll make an ether. And the other thing that we're going to do to help make sure that we don't have any acetate competing with that alcohol for the carbocation is we're going to use trifluoroacetate groups on the mercury instead. Trifluoroacetic acid is a much stronger acid than acetic acid. What that means is its conjugate base is weaker, and it's not a good nucleophile at all. It's more like sulfate and phosphate. Remember, we talked about the fact that some anions of strong acids are not good nucleophiles, and so the trifluoroacetate anion is a much worse nucleophile than acetate, and so that is another change that we'll make. Otherwise, this reaction looks a whole lot like the reaction that we did in the alkenes chapter. So here's an example of an alkene. It has 2 different degrees of carbon. So we're going to again do Markovnikov addition, and we're going to use the trifluoroacetate mercury compound, and this time they're using methanol as a solvent. And so at the end of the first part of the reaction, you've got the Markovnikov addition. Remember, the mercury goes on first to the less substituted carbon, and then the methanol acts as a solvent, and nucleophile is on the other carbon. And then when we put in the sodium borohydride, we get rid of the mercury and replace it with a hydrogen. So here's the product ether that you could have gotten starting from styrene. In this case, with cyclohexene, it doesn't matter which carbon gets what. The alcohol solvent we're using here is ethanol, and we'll put that on one carbon, and eventually the hydrogen will take the place of the mercury on the other carbon. Now, either one of these 2 examples could have been made by Williamson ether synthesis. If you think about it, remember that we could have used a methyl like iodide as a substrate, and then you would have had to have that alcohol on this carbon. But it's a little crowded, not too bad, but it probably would have been worth a shot. This one looks even more likely that it would have worked okay in a Williamson, because this part right here could have been the substrate attached to a halogen, and then we could have used cyclohexanol as the alcohol, and that would have probably worked just fine. But still, if you're not sure, then this reaction with the alkenes is always an option. And then there are some cases where you really do need to use the alkene route because you don't have the ability to do the Williamson because it's too crowded, there's no primaries or whatever. Something else, we talked a little bit in chapter 17 about phenols, special category of aromatic alcohols. And this carbon in the aromatic ring cannot undergo an SN2 reaction. And so if you wanted to make an aromatic ether, you pretty much are limited to which carbon can be the side that's the quote-unquote substrate side. So if you wanted to do a Williamson ether synthesis on this guy, this part would have to be the alcohol part, and then you can use a substrate that, in this case, if you're making this ether, a primary substrate is fine. That works okay for the Williamson ether synthesis. But you can also do the alkene route here, and all you need is just ethylene with this. Now, if I were going to propose to do this in a lab, I would probably go with the Williamson just because I don't want to deal with ethylene gas in a laboratory situation. But at least you can see that it could be done. So here's a problem that we want to make this ether is our target molecule. And so remember that we first have to look at the degrees of the carbon attached to the oxygen to decide whether we could do a Williamson or not. And it's constrained by being an SN2 reaction. So we have here this degree of this carbon is tertiary, the degree of this carbon is secondary, and this is starting to look kind of a little bit crowded. So maybe it's not the best route to try a Williamson on that. And so maybe this would be a good one to try for the alkene route, the oxymercuration. So now we need to think about that. What would that look like? So when you do the oxymercuration, remember, again, one side has to be an alcohol. So you can have this side be an alcohol, so then where would the double bond be in this part? Or you could let this side be the alcohol, and then the double bond would have to be over here, and it wouldn't matter whether it was here or here in that case. But part of the thing you have to decide is, remember that the oxymercuration is going to go by a Markovnikov addition, which means that the hydrogen is going to go to the less substituted carbon, and the oxygen group, in this case an alcohol, is going to go to the more substituted carbon. So you just need to make sure that whichever route you choose is actually going to give you the right product. In this example, it's really not too bad. You have a lot of choices. So let's say that we wanted to try making this bond. And so we'll see what our pieces have to look like. The alcohol on this side, and so there it is written in a line of type. And then we could have the double bond out here. And again, we asked ourselves, is this going to give us the right product? So this is the less substituted carbon, so the hydrogen is going to go here. The more substituted or tertiary carbon is going to get the alcohol group. And so this molecule would be a good starting material, and the product that we get out would be the one that we want. But that's not necessarily the only choice, because we could have had the double bond somewhere else in that molecule and it still would have worked. If you look at it, if you put the double bond inside the ring here, then this is the secondary versus tertiary. The hydrogen, the mercury first, then hydrogen would be on this carbon, and the alcohol would still end up here. So either one of these two alkenes would work to create this bond to make this ether with isopropyl alcohol. And they're both following Markovnikov's rule. So another thing that we could do is we could try making this bond. And so again, it doesn't matter whether you put the double bond here or here, it's the same difference. And so then we'd need this alcohol as our solvent. And again, just do a little check and say, are we following Markovnikov's rule, getting this alcohol, is this the right thing? And the more substituted carbon is getting the alcohol, and so that's right. Now, if you were going to do this in a lab and you're thinking about efficiencies and costs and so forth, probably one or the other of these molecules in this route, because this is a much more common and simple alcohol, would probably be the route I would choose. This stuff is a gas. This alcohol is not very common. So it will work, and of course that's the bottom line, is it will work, but if you think about it in practical terms, probably one or the other of these alkenes in this route would probably be the one that I would choose. All right, here's another example. So again, we want to look at the degrees of the carbons that are attached to the oxygen and decide about, how we might want to make this ether. And so we ask first the question, is it a good candidate for a Williamson ether synthesis? The reason I always start with that question is because that's really a pretty easy thing to do if it will work. But it is constrained by being an SN2, so that's just the question you have to ask. So we look at these carbons, and this one is secondary, and this one is primary. And it's not too crowded, so maybe we could use a Williamson to do this. One side is going to be the best one to use for the substrate. And this side is too crowded to be the substrate side. And if we're doing a Williamson, this is going to be a fairly bulky nucleophile, which could mean, it's a little problematic for the Williamson, but still it's worth a shot. So we might try that. And so we would take this alcohol, treat it with sodium hydride or sodium metal to make the alkoxide, the anion here, which is going to be the nucleophile to replace, substitute for this leaving group. So we could try that, and technically that looks okay. It's just this is a fairly bulky nucleophile, and so it might work, but you're never going to get 100% yields. So then let's see what else we could do. If we wanted to examine the possibility of doing oxymercuration, again, we've got to figure out one side's going to be an alcohol, and so we've got the opportunity to use this alcohol again. So if we did that, then where would we have to put the double bond? Well, if you want to get the oxygen on there, you could put the double bond right there, but is that going to give you the molecule that you want? You've got to take Markovnikov orientation into account when you figure this out. So if you tried this with the double bond right here, you see this carbon is tertiary, this carbon is primary. This carbon is going to be the one that gets the oxygen. And that's not going to give you the product that you want. Okay? So that's not an okay route. Well, all right, so that means that maybe we need to look on this side and see if we put the double bond in here somewhere, would we be able to do the oxymercuration? So if we put the double bond here, okay, so let's examine that. This is a tertiary carbon, this is a secondary carbon. Which carbon is going to get the oxygen group? It's going to be the tertiary carbon, right? So is that the product that you want? No, that's not going to give you the product that you want, so that's not okay. So we have one other possibility, which is to put the double bond here and ask ourselves that question. And so this is secondary, this is primary, so the oxygen would go to this carbon, and that is okay. So we have two routes that we could use to make this ether, and we have several ways that don't work, but we have two routes that are viable. So if you were trying to make this molecule, you might try both of these two routes to see which one works the best, and taking into account factors such as cost and availability of reagents and so forth. I don't know what the answer is, but you could definitely try both of those. Okay, so now we know how to make ethers. We know that ethers don't do a lot of reactions, so they're useful as solvents, and we've seen them as solvents in Grignard reactions, for example. But ethers do slowly oxidize in air, and so if you buy an ether, you're supposed to put a date on the container so that you know how old it is. And once it's been opened, then air can come into contact with it, then it can be oxidized slowly to a peroxide. And you maybe remember peroxides as being one of the things you could use to initiate free radical reactions. And peroxides themselves are not very stable, and sometimes they can be explosive. So what you're supposed to do if you have used up all of your ether is rinse out the container before you throw it away, because a lot of these peroxides are solids and they could be clinging to the bottom of the container. And so for safety purposes, you you don't want to keep your ethers for too long after they've been opened. You want to date the containers, and you want to rinse them out when you're done with them. But that's not a reaction that people do, to make peroxides. We have other ways to get to those. For hydrolysis of ethers, this is the main thing that we need to be aware of. It is kind of hard to hydrolyze ethers. They're not all that reactive, so if we're going to do it at all, we have to use really strong acid. And basically, it's going to be the opposite of how you would have made them. In other words, when they come apart. Whether they come apart in a reverse SN2 reaction would be dependent upon if you would have made it using an SN2 reaction. Then they come apart that same way. If you have an ether and the best way to make it would have been with an oxymercuration route, going through a carbocation, then that's probably the way that it will come apart. And also, those kind of ethers will be easier to hydrolyze. So we need to look at some examples of what I'm talking about. So here's an example of a hydrolysis. Now it takes a really strong acid, so either HBr or even more often HI, which is both of those are stronger actually than HCl, and reflux, which means boiling. Okay, you reflux water at 100 degrees, so boiling HBr or HI, and so what you're doing is you're setting up a reverse a hydrolysis reaction that's going to give you the opposite of the way you would have made this. Now, we talked about this particular ether a few slides back. So it could have been made by a Williamson SN2, and you had to use this as the alcohol because we could not do an SN2 on that position right there. And since the way this is going to work is the alcohol oxygen, the ether oxygen is going to get protonated and with the acid, and then you've got it set up to be a very good leaving group. And then the Br will be the nucleophile, and so it will react here and open this bond, and you get these two products. And aren't those exactly the same two starting materials you would have used if you were doing a Williamson ether synthesis to make this ether? Now, it doesn't matter which halogen you started out with. You could have used chlorine going that way, but like I said, we really need strong acid to take it apart. So here's another example, and with the mechanism. So here's this one's using HI. And so we protonate the ether, and then the nucleophile is going to approach the less crowded side, and this is a very good leaving group. Remember, oxygens are not good leaving groups unless they can leave as neutral molecules. So once you protonate that oxygen, then it's got the ability to leave as a neutral alcohol molecule, and so that makes it a good leaving group. And this is the SN2 step. And again, if you were looking at this ether and thinking, how would I have made that? This would have been your best option, to let this side be the substrate and this side be the alcohol. So you get back the same starting materials that you would have used to make it. Again, it doesn't matter which halogen you would have started with, but since we're having trouble breaking these apart, HI or HBr is going to be the halogen that you end up with when you take it apart. Now, if you have a tertiary carbon, or a carbon that can make a good carbocation, then it's not going to be one that you would have made by an SN2 reaction. And so it's pretty easy to take it apart, a little easier than it would have been if you would have made it with an SN2, because it can't come apart and make a carbocation spontaneously. But these guys, this tertiary carbon right here attached to this oxygen, could make a carbocation pretty well. And even the secondaries sometimes work. So it turns out it's going to be easier to do this, and so we don't really have to have HI or HBr and boiling solution. Also, if we want to kind of think about this as going back to where we started from, remember we had an alkene and an alcohol. If you want to get the alkene back, then you want to have a non-nucleophilic acid anion. In other words, if you use HBrHI anyway, you're going to get some product with substitution in there, but it's going to be an SN1. So if you want to get the alkene back, remember how we had modified that oxymercuration and used trifluoroacetic acid to make the acetates, the trifluoroacetates of the mercury, so that they wouldn't interfere? Well, we could use trifluoroacetic acid to break this apart. So this is how we might have made this molecule, with this alkene and this alcohol, and there's our mercury trifluoroacetate. And you know, it doesn't matter which carbon, which one of these carbons is going to get the oxygen is going to be this one, okay? And so, so we would have gotten to this product. So if you see that that's kind of the way you would have made it, then that's how you're going to take it apart. So the trifluoroacetic acid, again, you don't have to heat it up a lot. Once it gets protonated, it's going to spontaneously ionize, and then that will make a carbocation. Well, that carbocation, in the presence of this non-nucleophilic anion, is going to say, well, I can't wait forever for a nucleophile, and then it'll just lose a proton, and you'll get back your alkene. And that keeps things from being too many different products. Sometimes it can go either way. I mean, if you look at this example and you think about, well, how would I have made it? I mean, you might have made it with an SN2, Williamson reaction, because you have a primary carbon on one side of the oxygen. And so if you put in HBr, then you could use the Br as the nucleophile. But look what happened here. You could, as soon as you protonate this tertiary carbon could go ahead and spontaneously, this could form a carbocation and spontaneously ionize. If that happens, then the bromine will go ahead and attach there, and then you would get this alcohol. So if you get some kind of ether where you've got somebody who can go ahead and ionize, then you may not get exactly back what you started with because of that ability to spontaneously ionize. So this time it's going by an SN1 instead of either an elimination reaction or an SN2, which just complicates things a little bit. What does that mean? Well, that means that if you don't want that to happen and you do want the alkene, then you should use an acid here that has a non-nucleophilic anion, like the trifluoroacetic acid. Okay, what else? Well, in chapter on alkenes, we talked about making epoxides, and the industrial route for that was oxygen over catalyst, and that could make epoxides that way. Or we could use a peroxy acid, which I abbreviated RCO3H. They're showing you a specific example. So here's the R group, here's the R group, CO3H. Okay, so that's my abbreviation for that. And this is just one example. And you can make epoxides that way. And that was in the alkenes chapter. Or you could make a halohydrin. Now the halohydrin came from an alkene, and so here you go. This is actually an intramolecular Williamson ether synthesis. So when you use the base, and by the way, sodium hydroxide is strong enough because you've got this halogen, which is pulling electron density toward itself, makes this more acidic. So sodium hydroxide is strong enough base to make this anion, which will then come around from the other side and flip this out, and that's called an intramolecular cyclization because it happens within the same molecule. So that's what the word intramolecular means. So you can make epoxides that way. And these epoxides are very useful industrial chemicals. I think I've mentioned that before. And they can be opened up different ways. Their little three-membered rings are not very happy being three-membered rings, and we looked at this reaction also in the alkenes chapter just to sort of compare it to your ability to make either cis or trans diols. So if you have the epoxide and you put in an acid that has a non-nucleophilic anion, like sulfuric acid, for example, then it will protonate the oxygen, and then water will be the best nucleophile. It would come in from the opposite side, and so you would get a trans diol once this thing loses this proton. And that partnered with the reaction with osmium tetroxide, which would make cis diols. So we've seen that reaction already, and it is a type of an SN2 reaction, and it lets us open those epoxides. And if the epoxide isn't symmetrical, which of course this one is, then the nucleophile would come to the less crowded carbon side. Well, you could have other nucleophiles besides water, and so if you use HX as your acid in this case, then you have a nucleophilic anion, so we're assuming X is like a halogen. Then when this opens, the halogen is going to come from the other side, so you could get back to a halohydrin. Now what's interesting is that, remember I just said that the nucleophile is going to come to the less crowded carbon. And when we made halohydrins, if we had two different degrees of carbon here, the halogen would go to the less crowded carbon because it's the electrophile it goes on first. And so we would have the halogen on the less crowded carbon. When we open an epoxide with HX, the halogen ends up on the carbon that is less crowded but it's because it has to open up this ring. Anyway, it partners nicely with that other reaction. So let's see if we can make sense of that. Okay, here you go. Here's an alkene. And let's say that we do the halohydrin reaction. So we put in the chlorine in the water. So the chlorine goes to less substituted carbon, and the water goes here, and so you end up getting this halohydrin after you lose your proton. Okay, so here's the reaction. This alkene plus chlorine in water gives you this, and here's the mechanism. Okay, suppose you take this alkene and you make the epoxide with the peroxy acid. Then it protonates. Well, this can open up this ring, and you can get to exactly the same halohydrin. But this one is going through an SN2 also. Okay, so this one is two different ways to get to the same molecule. Because we're putting the chlorine onto less crowded carbon. Well, and that was an SN2 for that. But what if we have a tertiary carbon in there somewhere? So here's another example of an alkene, and this time I've used bromine. When you do the halohydrin, we're going to put the bromine on less substituted carbon, and so we're going to get this molecule right here. If we make the epoxide out of it, now this time when we put in the HBr, this thing gets protonated, it's going to spontaneously open because you can make a tertiary carbocation here. And once that happens, then the bromine will react there, and we'll get a different halohydrin. So whether you get the same halohydrin as on the previous slide or different halohydrins is really going to depend on the degree of the carbons again. I can't emphasize enough how important it is to pay attention to the degrees of the carbons that these atoms are attached to, so you know how things are going to come out. We won't see a lot of examples of this, but it kind of helps give you more and more examples of why we need to understand substitution reactions, why we had a whole chapter dedicated to those different mechanisms, because it impacts the geometry of things and the placement of the atoms along the way in subsequent reactions. Okay, so suppose you have this molecule and you react it with HCl. What is going to happen? Remember, you have an acid, so you look for the base. So here's a basic site in this molecule. So if you protonate that, then the question is, will the ring open by itself, or will it wait for the chloride ion to open it? And so one of these carbons is technically primary, and this one is secondary. So, you know, neither one is a super good carbocation, so maybe it will just wait. And this one is not crowded, so the chlorine could go there. So the first thing that happens is the protonation. We talked about the degrees of the carbon, and so probably it will wait, and the chloride ion is the nucleophile, and so we'll put it on the less crowded carbon, and so that's the product that we would probably get out. Okay, so ethers are fairly inert. Like I said, so far all we've seen them react with is acid, and actually a lot of them are stable to mild acid, and it takes fairly strong acid to get them to work, to open up or go through hydrolysis. Except for the epoxides, they're pretty reactive. Easy to open up with acids or bases. Most ethers don't react with bases or nucleophiles, but the epoxides do because of the ring strain. And we've just looked at examples where the nucleophile will react with a less crowded carbon. Now, we were using acids to open up epoxides, but we don't have to use an acid. We could use a base. So we could put in hydroxide, and it will go to the less crowded carbon, and it will open it up, and if we put in some water, we can make a diol out of that. So you could make a diol out of an epoxide with either acid in aqueous solution or base in aqueous solution. And in fact, this is how you get into polymers of these things. If you don't have but a catalytic amount of base, then this guy could be the nucleophile, another one, and there you go, you start making polymers. Here's another example. So nobody said it had to be OH or water. It could be an alkoxide. So we can react at the less crowded carbon, and we can make different ethers out of that. And we have all kinds of things that could be the nucleophile in this case. An amine could be the nucleophile and go to the less substituted carbon. So you can make molecules like this. Metoprolol is used as a blood pressure, something to do with blood pressure and controlling blood pressure. So this last step in its synthesis, or next to the last step in its synthesis, is an SN2 on opening this epoxide, and then the hydrogenation gets rid of this, which we haven't talked about that kind of reaction. It's just kind of an oh my thing, but they wanted to show you that the reason that they were doing that reaction was to get to metoprolol. You can also use carbon nucleophiles, and a Grignard can be a carbon nucleophile. So here's a Grignard reagent, and we've talked about them a lot in Chapter 17, and it can react with an epoxide ring to open it up, and you get a molecule that's 2 carbons longer. Now, technically, any epoxide would react with Grignards. It turns out that sometimes there's some other things that can go on that lead to some rearrangements. So mostly people don't do Grignards on epoxides unless they're very simple ones like ethylene oxide. And one other thing I want to say about this is that I taught you that the little, what I call litany, that if you have a product and you look at it and wonder, could I have done a Grignard, you look at that and say, the carbon that has the OH on it was the carbonyl. Well, in this case, that's not quite right. The carbon that has the OH on it was part of an epoxide. And not to say you couldn't make this molecule using a carbonyl compound. It's just you get two carbons on here all at once by using this. And otherwise, primary alcohols, you'd have to use formaldehyde if you had a chain of things. And so this is nice because you get two carbons at once. So keep that in mind. The carbon in the Grignard is a very good nucleophile for this guy also. Something that's kind of interesting, different kind of ether, I had one of these in the nomenclature slide. These are called crown ethers, and they can trap a cation inside of here. And it depends on which ether. Now, the name of the ether is, this is the total number of elements in the whole ring. So if you start here and go around, you're going to get 18 atoms. It's a crown ether, and 6 of these atoms are oxygens, and so that's where this name comes from. Well, so what cation they can trap in here depends on how big it is. So if you had 15 crown 5, a sodium ion would fit in there, 18 crown 6, a potassium ion fits in there. And so you get the idea. And so they can be desalination agents. The downside, of course, is getting your hands on them. They're not super cheap, but still that's one of the research areas that people are working on, because if you trap the cation inside of that hole, then the anion has to go too, because it can't be left by itself. So that might be one thing that eventually we could commercialize, to use those as desalinating agents. Another thing that they can do is they can be used as models for biological systems. If you think about it, hemoglobin has 4 nitrogens, not 6, but 4 nitrogens, and they hold an iron in the middle. And chlorophyll holds a copper, and those things all have this kind of feature. We've got some electronegative elements with the electrons pointing into the middle, and there they can hold a cation. So this one fits potassium. Okay, so we have a little bit of information to talk about regarding sulfur compounds, and these thiols are the analogs of alcohols, and so the nomenclature is going to go similar to the way alcohols go, as long as it's the only functional group. And you'll also hear the old common name mercaptan sometimes used, and that's the basis for the group name. So if you had just a simple molecule like this, ethane thiol, so it's just very similar to the alcohol name, or cyclohexane thiol. And here's the group name. So in this case, the aromatic ring is considered the parent with the carboxylic acid, and so we needed a group name for that, and so that's where the mercapto comes from. Thiols are the methane thiol, or methyl mercaptan is the common name, is the odorant they used in natural gas. So when you say you smell natural gas, you don't smell methane. What you smell is methyl mercaptan. And so you get the idea. These things don't really smell very good. And skunk is also a mercaptan. And these thiols are a little bit more acidic, and they're also better nucleophiles than their corresponding alcohols. So we're going to look at just a couple of ways to make these that are both SN2 reactions. So we won't see a whole lot of opportunities to make various molecules. But one thing you might be interested in is why we want to do that. And there are a lot of other biological systems that use thiols. This molecule right here is cysteine, which is one of the essential amino acids. You notice that it's a thiol. And we'll talk a little bit more about that later. So kind of the no-brainer route is just be to do an SN2 with the bisulfide ion, which is analogous to hydroxide. And so you can buy sodium bisulfide, and you could use this as the nucleophile, and you could make thiols out of that. And it has pretty good yield. The problem is that once you get this is also a good nucleophile. So you might start having a competition where some of these guys find some of this starting material and you just make bigger and bigger molecules. And you might not want that. So one of the things that people do is look for ways to cut down on that side reaction. And one option is to use a large excess of the sodium bisulfide so that it's more likely that this guy would see that as the nucleophile. But there's one other possibility, and that is to use thiourea as the source of the sulfur. So we need to take a look at that. So this molecule right here is thiourea. Now you know of urea as a waste product from the degradation of proteins in the body. And urea has an oxygen here. Okay, so you can make thiourea from regular urea, and this sulfur is still fairly nucleophilic, even though it's in this double bond. It's kind of like a carbonyl. It can be the nucleophile, but it can only do it one time because you're going to get some resonance stabilization here, but nevertheless that sulfur has a lot of positive character. So this guy's not going to compete with this for nucleophilicity on these molecules. And then once you've finished and you get rid of all of this, then you do hydrolysis and you free up the thiol. So this is good because this stuff is cheap, and you can recycle the urea if you need to back to this, and you just are sure that you're going to get a thiol and no competing multiple occurrences of chunks of carbon on your sulfur. So why do we want thiols? Well, I mentioned cysteine as an essential amino acid, and what happens in the body is that molecules of thiols are oxidized to disulfides, and the body doesn't use iodine as an oxidizing agent, and you may not be used to seeing iodine as an oxidizing agent, but it's a very mild oxidizing agent. Halogens go from 0 to -1, and so they're getting reduced, so something else is getting oxidized. In this case, it's the thiols. And it's also pretty easy to take the thiols back to the disulfides back to free thiols by some kind of reduction. Now remember, in the book, they're going to show you these two reactions, and these two arrows are going to be kind of close together, and it's going to make you think about equilibrium, but this is not an equilibrium. This is a reaction that goes in this direction, this is another reaction that goes in that reaction, and they are partners. Okay, in the body we have different ways to oxidize and different ways to reduce, but nevertheless it's a cycle that can happen in the body, and it can happen to strands of proteins that are outside of the body, like on your hair. So here's an example of a biological this is a piece of a biological molecule, and there's a cysteine right here. Okay, this part of this peptide is a cysteine. Okay, and so there's its free thiol, and here's another one. And so if those get oxidized, so here we're using peroxide, then they will join together and make a disulfide linkage. Well, that could also be reduced, and this is a biological reducing agent, back to the free thiols. In hair, we do this in the beauty parlor. We go in to get a perm, and our hair strands are linked together with disulfide linkages, and so they put on the perm material, breaks these apart, so it's going to do a reduction. And then they wrap the hair around the rollers, and then they put on the fixer, which oxidizes them back. Well, what happens if they don't find each other? And now they're lined up differently. Well, that's why your hair gets brittle, because not all of those thiols find each other to make disulfide linkages again. And the more times you get your hair permed, the weaker it gets. One other thing in this chapter is a little bit of information about sulfides, which are compounds that are analogous to ethers. And so the nomenclature goes kind of like you would expect. These two are the same, so we can use dimethyl, and then the word for this group right here is sulfide. Or if you have two different groups, you put them in alphabetical order. Methylphenyl sulfide. If you look at this as the alkene being the parent, then this is a group name, so it's a methylthio is the group name for that. You can make these from thiols pretty easily. In fact, we talked about how we had to work not to make those because the sulfur was a good nucleophile. And so we can do SN2 reactions to get those guys. And you don't absolutely have to have an anion, but if you do, you can get from the SH, remember that's analogous to phenol. Those are pretty acidic. These are even more acidic. Okay, so you just put in some sodium hydroxide, you can make this anion, and then do an SN2 reaction, and you can get a sulfide. An interesting thing about sulfur is it can take more bonds than oxygen can. And remember we talked about the sulfur in thiols being a good nucleophile. Well, even sulfide sulfurs are good nucleophiles. And so you can make salts out of these things, much more stable kinds of salts than oxygen. When oxygen takes 3 bonds, it gets a plus charge. Not very stable. Hydronium ion, sure it exists, but it's in equilibrium. And there are not a lot of oxonium salts that you can actually isolate and keep. Not so with sulfur compounds. These things are pretty stable. And not only that, sulfur can oxidize some more. So you can take your sulfides and you can oxidize them to sulfoxides. Now, one of the molecules you may have heard about is dimethyl sulfoxide, which is also called DMSO. We used it as a solvent a couple chapters back. Well, you can use peroxide to oxidize these guys to the oxides. You may also see this written with an S with a plus charge and an O with a minus charge. It's the same thing. It's just whether you want to follow the octet rule or violate the octet rule in your drawings. And then this is a peroxy acid. Now, what we used peroxy acids for previously was to make epoxides. So this is a stronger oxidizing agent, and so you can make sulfones out of it. And again, you might see the sulfur with a +2 and the 2 oxygens, each with a minus charge. And that would be another way to draw a sulfone. And these things, not so useful. There's a few of those around, but these are pretty common. And so it makes sense that if this is a stronger oxidizing agent, you could actually go from here directly to here with just enough of this. And here's a picture of DMSO I mentioned. It is used as a solvent. It's the best known sulfoxide, and people have used it for medical purposes, and it's supposed to be good for arthritis. The problem is that it's such a good solvent that anything you put on your skin, if you put DMSO on your skin, anything else that's on your skin will get dissolved right through your skin along with it, which might not be good if your hands or your elbows aren't clean and you're rubbing this stuff on there. So here's a little bit of review. Let's say that you have this molecule and you want to make this molecule. And you see what we need to do here is we need to change this functional group, which is an ester, into this group. You notice we still need the carbon, and we need to swap out some oxygens and get this sulfur in here. So we need to think about what we might do with things that we know about. And in the alcohol chapter, we learned one of the things we could do with esters was be to reduce it. And that's pretty much the only thing we know about esters at this point, so that must be one of the things that we need. So let's go forward and think about that. So we're transforming the ester, and the only ester reaction we've studied so far is reduction. We're not changing the number of carbons except in the chain. We are getting rid of this carbon, okay? And so if we reduce the ester to an alcohol, how do you do that? That's with lithium aluminum hydride. So we can reduce this ester to the alcohol with lithium aluminum hydride. Now what we need is to change this OH into this SH. So if we do that, then we're probably going to have to go through some other reaction because we can't directly change the OH into the SH. Can you think of what that is? It's not a good leaving group the way it is. We need to make it into a good leaving group. So what we could do is we could change it into a halogen. If we do that, then we can do our SN2 reaction to put in the sulfur. And we can do that with the thiourea, and we can get that reaction. Okay, so when you go through these kind of problems, synthesis problems, the approach of, where you start kind of depends on how you feel about things. So I thought it might be instructive to try this problem a different way. I'm trying to help you kind of see how to think about things. So in this case, we started from the ester and thought about what we knew about esters, and then we proceeded. What we need to do differently now is we need to try working the other way. In other words, let's think about the thiol first, and what do we know about how do you make thiols? And so we'll approach it philosophically kind of a different way. So what do we know about how to make thiols? Well, so far we only know that we can do SN2 reactions, and we can do those SN2 reactions on molecules that have an uncrowded carbon and a leaving group. And so we've got that situation here. So we need to think about what would be the precursor to the thiol and what do we want to use for the source of the sulfur. So we learned that you could use excess sodium bisulfide, and you could also use the thiourea route. And either one of these are technically okay, although this one sometimes has problems with side reactions of extra groups going onto the sulfur. So we need a substrate to put that with, and that would be the rest of this molecule attached to an appropriate leaving group. So whatever leaving group you want to use. So here's an example. So we have the right carbon skeleton, we have a leaving group, and now we just need to put that together. So we need to do this reaction. Again, I've chosen to use the thiourea route. Okay. So now what we think about is, okay, so where did this come from? And remember, we have to ultimately have come from an ester. So where did this come from? And what does that have to do with esters? And we can't get directly from an ester to this halide, so we have to think about that. It can't have been just one more step back. We have to think about how do we get something to here. And so this was the starting material that we have to start with. So how can we think about this molecule and getting to here from something that's got a closer relationship to the ester? And so the answer to that question was no. So what can we make halides from? If we can't make them from esters, we could make them from alcohols. We could also make them from alkenes and alkanes, and so we have to decide which one of those things we like best. And the alkanes route, remember, that was the free radical halogenation, and that was pretty uncontrolled. In the alkenes chapter, we talked about turning an alkene, but then you lost the alkene. In chapter 10, we also talked about allylic bromination. You might say, well, okay, we could do allylic bromination if we had the 4-carbon alkene. We could get the bromine here, but then some of it would also go here. So that might not be as good if we came from an alcohol, or from an alkene, and we were trying to get just this molecule, that might not be so good. But if we came at it from an alcohol, we could just have an alcohol here and do a swap. And that sounds more like something that's closer related to an ester than an alkene, also somewhere else in this molecule. So I'm going to guess that alcohols might have been the desired starting material for getting from getting this molecule from an alcohol. So if we have this alcohol, we can get to here. And now, when we see that, we say, okay, so is there a way to get to an alcohol from our given starting material? And we do know a way to do that. And so we can get to here because we have the same number of carbons in the chain as we do in this alcohol. All we have to do is a reduction to get to this alcohol. And so we don't have to make any new carbon-carbon bonds. We do have to do a reduction. And so that's reduction is the process. And how many levels of reduction is that? Well, this carbonyl is in a level which is 2 levels different from this carbon. And so we need a really strong reducing agent to do that. And so that would be lithium aluminum hydride is what we would have to use for that. So I have talked about 2 different sort of philosophical approaches. Yeah, I use the same stuff in both approaches, but I sort of trying to help you think here, kind of how you could think about these things, whether you're kind of starting at this end or that end when you're given a particular starting material. All right, so for this chapter, you need to know how to name ethers, and you need to also be able to recognize thiols, sulfides, sulfoxides, and disulfides. And you need to be able to make ethers by either the Williamson ether synthesis or by oxymercuration, and you need to understand when you would use which one of those. And remember, that was looking at the degrees of the carbons attached to the oxygen. That would help you. And you need to know really the only reaction of ethers is their hydrolysis, and it's pretty much like the reverse of how you would have made them, and it takes a strong acid to do that. And then we talked about epoxides and opening epoxides, and particularly the ring opening reactions with various nucleophiles. And we talked a little bit about thiols and sulfides and different levels of oxidation levels of sulfur that it could take, and that made it different from oxygen. Okay, so in preparation for the final, you need to go back over all of your exams and try them again like a test. Try not to look at what the answers are, and try not to look at the book or what you put before, and just think about each question, and then you have something to check it with. And probably what you're going to see is that you really have learned a lot. You should be a lot more comfortable with the material from the first couple of tests than you were probably at the time. And also you'll know if you keep missing the same thing over and over again, then you know what you need help with. And that's when you go to come to me, or you go to the tutoring center. Wherever you go to get help, you know specifically what to get help about. And make sure you do the online quizzes, and if you're doing OWL or sapling, whatever, work on those quizzes. And I'm giving you some synthesis homework, and that will help you review the reactions. And so the last thing that I just did in this chapter was different philosophical approaches to the synthesis problems, which will be of that nature, where you're given a particular starting material and you have to turn it into whatever your target molecule is. And there will also be a comprehensive online quiz. In terms of short answer, there will be some short answer on the test, and they will be similar to the short answers that you've had on the front page of the exams. So you need to understand how to draw mechanisms and reaction energy diagrams and things like that. And there's more information about kind of overview stuff in the Blackboard in the study guides for all chapters.